Welcome to lesson 2.5. We're going to be talking about zeros of polynomial functions. Let's take a look at the objectives. The rational zero theorem to find possible rational zeros. That is something we did in Algebra 2, so we'll look at that. We're going to find zeros of a polynomial function. So we're going to review how to do that. That's going to involve using synthetic division and then solving quadratics, like we learned in Algebra 2. Basically, same with solving. And then use the linear factorization theorem to find polynomials with given zeros. That is new, and we'll take a look at that. All right, so the rational zero theorem. You can read all that. Basically, if you recall, the part that's important is P is a factor of the constant term, right? So whatever is the last term. And Q is a factor of the leading coefficient, so whatever is the first term. So the rational zero theorem says that if a function has a zero, a rational zero, then it's going to be a factor of something from P and something from Q, something divided by Q. So let's take a look at that in practice. So what that's saying is if the factor in part A, well, your P is 6, so what are the factors of 6? 6 can be 1 and 6, or 2 and 3. In this case, Q is 1, so it's just 1. So then it's all of these numbers divided by that number. So it's really just all of those numbers. Also plus or minus. So for part A, the possible rational zeros of that function are plus or minus 1, 2, 3, and 6. Part B is a little trickier because the Q value is 15, so that actually has some factors. So let's take a look at that one, and then I'll let you guys try C on your own. So let's look at 2 first. Factors of 2 are just 1 and 2, right? For 15, you've got 1 and 15, 3 and 5. That's it, right? So it's all the factors of 1 and 2 divided by all the factors of 15. So for the possible rational roots for this one, 1 divided by 1 is 1. So that's plus or minus 1. 2 divided by 1 is 2. Right, 1 divided by 15 is 1/15. 2 divided by 15 is 2/15. 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. And then 1 divided by 5 is 1/5. And 2 divided by 5 is 2/5. So again, it's all the factors of 2 divided by all the factors of 15 in combination. So again, if this were to have a possible rational root, it would be one of those. Why don't you pause it now, try C, and see if you come up with the same numbers that I do. So all the factors of 3 are 1 and 3. All the factors of 4 are 1, 4, and 2. 1 divided by 1 is 1. 3 divided by 1 is 3. 1 divided by 4 is 1/4. 1 divided by 2 is 1/2. 3 divided by 4 is 3/4, and 3 divided by 2 is 3/2. Keep in mind, if you made a mistake, I'm assuming what it would be is that you're also doing factors of 4 divided by factors of 3. It only goes one way. It's just the factors of the constant, which is P, divided by factors of Q, which is 4. So, for instance, if you had 4 divided by 3, that's flipped. It's the wrong way. So like 4/3 would not be part of your list, for instance. All right, let's take a look at the next one. So here's where it's saying to find all the zeros. So not just what are the possible rational zeros, but find all the zeros. So what I'm going to do is come up with that same list of possible rational roots. All right. So for part A, factors of 6 are 1, 6, 2, and 3. Factors of 1 are just 1. So all of these divided by 1 is just going to be all of those, right? So possible rational roots in order are plus or minus 1, 2, 3, and 6. And keep in mind, this is not just asking what are the possible rational zeros, it's saying find all the zeros. So now we at least have it narrowed down to what are the possible rational ones. What I'm going to suggest now is to get out your calculator. So, all right, so once I have my calculator out, what I'm going to do is graph the function that we're doing first. And instead of just randomly guessing which one of the possible rational zeros it could be, I'm going to see if I can observe it and know where to start. So x cubed plus 2x squared minus 5x minus 6. Let me graph. So if I look here, it looks like it's crossing at -3, it looks like it's crossing at -1, and it looks like it's crossing at 2. All of those were on our list, right? So now just basically pick one of those and do synthetic division with it. I'm going to pick 2, just because it's positive. All right, so if I pick 2, put 2 in the box, synthetic division, have then coefficients of 1, 2, -5, and -6. Drop the 1, 2 times 1 is 2. Add down, you get 4. 2 times 4 is 8. Add down, you get 3. 2 times 3 is 6. Add down, you get 0. The fact that we got that 0 there means what we saw in the graph was accurate, that it is crossing at 2. So that means one of the zeros for part A is 2. How do you get the other ones? Well, you could keep doing synthetic division. However, what comes out of this is going to be x squared plus 4x plus 3. The other two zeros of part A are the two zeros of this function. So I'm just going to factor this. And we get x plus 3 and x plus 1. If I set them equal to 0, I get x equals -3 and x equals -1. So the other two places it was crossing when we looked at it on the graph. So the graph is super helpful. But the answer to this is the zeros are 2, -1, and -3. All right, at this point, I want you to try part B on your own. So pause, give it a try, see if you come up with the same answers that I do, and I'll be back with answers. So for this one, it only has 4 possible rational roots, plus or minus 1 or plus or minus 3, because it's the factors of 3 divided by the factors of 1. So those are your 4 options. When I graphed it, I could see that it was crossing at -3, but it was also crossing somewhere to the left of that, which looks like it might be -4, but it's not one of our possible rational roots, so it couldn't be -4. And then this one looks like it's crossing just right of 0, so a little more than 0, but certainly not an integer. So -3 seemed like the logical place to start for me. So I did -3, did synthetic division, got the remainder to be 0, which is what I was looking for. The resulting function that comes out of it is x squared plus 4x minus 1. Pretty easily, you can tell it's not factorable, right? Because there's nothing that multiplies a -1 and adds to 4. So I did quadratic formula. I found the discriminant to be 2 root 5. And then it's -4, because it's opposite of b, plus or minus 2 root 5 over 2, which simplifies to -2 plus root 5 and -2 minus root 5. So those are your 3 zeros, are -3, and then plus, well, -2 plus or minus square root 5. So those are the 3 zeros because the plus or minus obviously accounts for 2 different ones. All right, let's take a look at the next example. All right, a couple properties of roots of polynomial equations that are going to help us here. Step 1 here says if a polynomial equation is of degree n, then counting multiple roots separately, meaning ones that have a multiplicity of more than 1, the equation has n roots. So whatever the degree is, it's going to have that many roots. The two that we just looked at were cubic functions, and they had 3 roots apiece, right? That's going to happen every time. So if it's a 4th degree, it'll have 4 roots, for instance. The second part here is if you have an imaginary root, its conjugate is also a root. So if a plus bi is a root, then a minus bi is a root. For that matter, which we're not talking about here explicitly, but is also true, if you have um, an irrational root, the same thing would occur. An irrational root would also have a conjugate be a root as well. Okay. So the fundamental theorem of algebra says if f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. All right, so basically what it's just saying is you have at least one root, and as we were talking about on the previous screen, um, you're going to have, typically you're going to have the amount of roots that the degree is. We're going to look at this. Complex numbers are just all-encompassing of the real numbers that we spent most of our lives talking about. Imaginary numbers are also included in that, but complex numbers include real and imaginary numbers. And that's what we're looking at here as well. So integers are inside rational or inside real, which is inside complex. The linear factorization theorem, a little complicated to look at, but I'll just break it down a little more simply. But basically what it's saying is, if you have this, whatever the polynomial function is, you can break it down into the amount of linear terms that are going to get multiplied together as the degree. So there's going to be the same amount of linear factors as the degree of the original function, which is essentially what we just talked about with the number of zeros, because the number of zeros and the number of factors are going to be the same. And see how it says possibly real? So that means some of these could be imaginary and not necessarily distinct, meaning some of them could repeat if there's a multiplicity. All right, so let's take a look at this first example here. Well, the first example using this theorem. So here's what it tells you. It says it's 3rd degree, so that means there's going to be 3 factors in the end. And it's telling you it has a real coefficient. Well, it has a real 0 at -3, and it has 1 at I. It's only telling you 2 of them, but we know that there's going to be a third, right? Because since it's 3rd degree, there has to be 3 zeros. Well, that's where it comes into play, that factor we're talking about, where the imaginary roots come in pairs of conjugates. So if I is a root, is a 0, then -I has to be as well. So if I use that linear factorization theorem, x minus -3 is one of the factors, so x plus 3. X minus I is one of the factors. And x minus -I, so x plus I, is one of the factors. Right? So I know that a sub n times those 3 factors, and a sub n is just going to be like your coefficient out front. And that's something we have to figure out at the end. But at least I know that those 3 factors are part of the function. If you FOIL together x minus I and x plus I, that's how you get the x squared plus 1. If If you FOIL together x plus 3 and x squared plus 1, that's how you get x cubed plus 3x squared plus x plus 3. We still don't know what a sub n is, but that's where this fact is going to come into play. If f of 1 is equal to 8, that means we can substitute 1 in for x and 8 in for the y and solve for a sub n. And that's what we're going to see on the next slide. So we're substituting 1 in for x, and we're setting it equal to 8. All right, so that's a 1 in there, and then this is an 8 here. 1 plus 3 plus 1 plus 3 is 8. So 8 times a sub n is equal to 8, which means a sub n is equal to 1. So that would be what you would, if a sub n ended up being a different number, you would multiply it in to that factor that we figured out, the x cubed plus 3x squared plus x plus 3. Since it's 1, you just multiply in 1, which is nothing, and you end up getting that the equation is f of x is equal to x cubed plus 3x squared plus x plus 3. So normally I would probably just ask you to try this one on your own. I'm guessing maybe you're not quite ready for that. So I'll work out this one with you, and then I'll have another one available as an exit ticket. That's how we'll do it. So this is basically the same question as the last one. This time it says it's a fourth degree, so that means I know there's going to be 4 factors that we're going to multiply together. In this case, one of them is -2, one of them is 2, all right, and then one of them is I. The fact that one of them is I means, again, negative I is also 1. So those are the 4. I expected there to be 4, and those are the 4. When I go to write the function now, it's f of x is equal to a sub n times each of these zeros in factor form. So what I mean by that is x minus -2 would be x plus 2. X minus 2. X minus I. And then x minus negative I, so that would be x plus I. Now I'm going to FOIL all those together. I think it would make sense to do the first two together, then the second two together, and then multiply those results together. So x times x is x squared. X times -2 is -2x. 2 times x is 2x. So that would add to 0. And then 2 times -2 is -4. And then x times x is x squared. X times I is ix. Negative I times x is negative ix. So that would add together to 0. And then negative I times I is negative I squared. But remember, negative I squared is -1. So really it's going to be plus 1. All right, because remember, I squared is -1, so minus I squared would be then minus -1, so plus 1. Now I'm going to FOIL these together. So x squared times x squared is x to the 4th. X squared times 1 is x squared. -4 times x squared is -4x squared. -4 times 1 is -4. I can add those middle terms together and I get x to the 4th minus 3x squared, and then -4. So all of that is still getting multiplied by a sub n. So the question is, what is a sub n? Well, now that's where this part's going to come into play. I can substitute the 3 in for x and the -150 in for f of x. All right, 3 to the fourth. Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. So we've got 81. 3 times 3 is 9, times that negative 3 is negative 27. 81 minus 27 is 54. 54 minus 4 is 50. So now I've got, let's write it up here, negative 150 is equal to 50m, 50a sub n. So when I divide by 50, I get a sub n is equal to negative 3. So now when I go back to that original function, a sub n is negative 3. So I'm going to rewrite that as f of x is equal to negative 3 times x to the fourth minus 3x squared minus 4. If I multiply that negative 3 in, I get f of x is equal to negative 3x to the fourth plus 9x squared plus 12. And that would be your answer there. So again, your exit ticket is going to be another one of these. Okay. And let me reach out if you have any questions.